Hello all. I believe Unit 1 is taken this Friday, so I'm sorry if this video comes a little bit too late, but I'm working on multiple things, so I'm trying to do my best here, okay? So this is a past paper from October 2025. As you can see, it's Unit 1, and we will dive in immediately just because I want to watch the Champions League semi-final that starts in about 3 hours. So yeah, I want to watch that. It's Arsenal versus Atletico Madrid. I don't support any of the teams, but I am into football, and yeah, I watch. So, the what's going on with this? I always switch it off, and it always comes back. Okay, I mean, it checks the spelling and it suggests auto corrections and such. Anyway, let's dive in. Okay, section A, 10 multiple choice questions that award 1 mark each. As I say in most of my videos, you should approximately use a minute per mark. So if a question awards 10 marks, it should take you 10 minutes. Always work on things that you know first, so that you build momentum to come back to problems that you don't know how to solve immediately in the end. Okay, so work on everything you know and then come back for the questions that you don't know. Okay, question 1. Which of the following is a unit for a vector quantity? Okay, joules, kilograms, and watts are scalar quantities because energy, mass, and power are scalar quantities. They don't have a direction. The only quantity that does have a direction is force, which is measured in newtons. So the option C is the correct one. Okay. Okay, question 2. A lamp has a constant power input and constant efficiency. Which row of the table describes how the useful power output and total energy output vary with time? I'm gonna need the clean page to explain this. So efficiency, this question 2, right? So efficiency is given by useful power output over power that is input. Okay, so we see that the useful power output is given by the efficiency times the input power. So this does not depend on time. Okay, so useful power output is constant, right? Because nowhere in this equation, the one that I box in red, okay, nowhere in this equation do we have a time dependence. Okay, so that's that. And now if we go back to the table, we see that options C and D are automatically wrong. Okay, so it's either A or B. Now, how do we find the total energy output? Okay, the total energy output can be found by the following. So the output power, which is the useful power output, okay, so this thing is used over there, okay, is given by energy over time, right? So the energy, the output energy, is given by the output power, which is constant in time, times time, okay? So this will keep increasing with time. So energy out will keep increasing as t increases, okay? I hope this makes sense. If it doesn't, ask me. I always reply. So B is the correct answer, okay? I hope this makes sense. Question 3. Which of the following is always true of the forces in a Newton's third law pair? So the forces act on the same object. Totally wrong, because this is what we use as a counterexample of forces that are not a Newton's third law pair, okay? B, the forces act in the same direction. Again, obnoxiously wrong, because they have to act in opposite directions. C, the forces cause acceleration. This is irrelevant, right? And D, the forces have the same magnitude. That's the correct answer, okay? They do have to have the same magnitude, but opposite direction, okay? So we can move on now. Okay, question 4. A ball bearing falls through oil at the terminal velocity. Which row of the table is correct when the temperature of the oil decreases? So for the viscosity, as the temperature decreases, the viscosity increases. And you can think about honey, okay? If if we actually increase the temperature of honey, it flows like water. But if it's really cold, it doesn't flow at all, okay? This means that the viscosity increases, and the same is true for oil. Now, about the terminal velocity, the Stokes force is going to be increased if the viscosity gets higher. So F Stokes increases as the viscosity increases. So the velocity decreases because the ball bearing will experience more force, more drag force. So the terminal velocity will decrease. So the option C is the right one. Okay. Okay. 5. A balloon moves upwards at terminal velocity. The forces acting on the balloon are upthrust, viscous, drag, and weight. Which of the following statements about the magnitudes of the forces acting on the balloon is correct? So let's first draw the balloon. Okay, so we draw it as a point particle. It experiences an upthrust when it flows up in the air. The drag is actually in the opposite direction. Don't forget that, because it moves up, right? So the velocity is up. So that's the upthrust, the drag, and of course the weight. Okay. So for terminal velocity, we need the upthrust to be equal to the drag plus the weight. Okay. So we can immediately eliminate options A and B are totally wrong. And then we are left with option C. If the upthrust was smaller than the drag, it will go down, right? So the only correct option is D, because you can see it from the equation. If the upthrust is equal to the drag plus the weight, then the upthrust is definitely higher than the weight, larger. Okay, so we can move on. Question 6 is a trick question. Okay, it tricked me in the beginning, and then I was like, wait, something's wrong here. So let's read it. A plank of wood has has weight W. The plank rests on 2 supports. The forces from the supports on the plank are Fa and Fb as shown. Which of the following vector equations, okay, that's the key, gives the relationship between Fa, Fb, and weight? Okay, so options A and B are totally wrong. I mean, just by inspection. I mean, in A, they subtract the forces, that's wrong. In B, they subtract the second force, Fb, from weight. But it's weird. So C and D look correct, and C appears to be the correct answer, right? But no, it's actually wrong, because these are vectors, okay? So because we are working with vectors, we have to sum them up. So the sum of the 3 vectors is actually 0, okay? And if you work with the magnitudes of these forces, then of course you're going to have Fa plus Fb minus W is equal to 0, okay? But because you are working with vectors, you have to add them, okay? So vectors are quantities that you add up. So D is actually the correct answer, not C. Let's do 7. A student uses a piece of string to attach a mass of 0.4 kilograms to a mass of 0.5 kilograms. She then places the string over a pulley as shown. Okay, which of the following gives the acceleration of the 0.5 kilograms mass in meters per second squared? So I'm gonna need an extra page for this one. So this is the situation, the pulley, and we have a string attached here, and we have the 0.4 kilograms mass. And then we also have the 0.5 kilograms mass on the other side. So let's draw the forces. So there will be the tension from the string, which is going to be the same for both masses. And then let's use red. We're going to have 0.5 times g for the weight of the first of the 0.5 kilograms mass, and 0.4 times g for the second mass. Okay, so these are all the forces. Because the 0.5 kilograms mass is the heaviest, the system is going to move in this direction. So the acceleration is going to be down for the 0.5 kilograms mass and up for the 0.4 kilograms mass. Okay, I hope this makes sense. And this acceleration is of course going to be the same for the two masses. Okay, now let's write down the forces. For the 0.4 kilograms mass, this Newton's second law is going to be t, because it's in the same direction as the acceleration, so it's going to be taken as positive. So t minus 0.4 g is going to be equal to 0.4 kilograms times the acceleration, right? For the 0.5 kilograms mass, we're going to have 0.5 we're going to have 0.5 times g, because the acceleration is now down. So 0.5 g is a force that is in the same direction as the acceleration. So 0.5 times g minus the tension is going to be equal to 0.5 times a. Okay, and we can sum these equations, right? And if we sum them, the tension goes away. Okay, so that's a nice cancellation, and we get 0.5 minus 0.4 g on the left hand side, and on the right hand side we have 0.5 plus 0.4 times a. So a is going to be 0.5 minus 0.4 times g over 0.5 plus 0.4. Okay, so this definitely needs more than a minute to solve, maybe 2 minutes, 3 minutes, I don't know. Let me know in the comments. And also subscribe, guys. 85% of the people who watch these videos are not subscribed, so it's really sad. So it doesn't cost anything. I'm not asking for anything. So it's yeah. Anyway, if we go back, we see that the correct option is B. Okay, and this was a hard problem, I think. So we are ready to move on. Okay, question 8. The table shows information about two wires made from different metals, wire P and wire Q. They have the same length, different cross-sectional area, and Young modulus. A tensile force applied to P produces an extension delta X. The same tensile force is applied to Q. Which of the following is the extension of Q? So we have that sigma, the stress, is equal to the strain times the Young's modulus, right? But stress is force per cross-sectional area, and strain is extension over length times the Young modulus. So delta X in general is equal to the force times length over the Young's modulus times the cross-sectional area. Now for P, delta X P is going to be equal to the force times the length over the Young's modulus times A. Okay. Now for Q, delta X Q is going to be F. It's the same force times L. It's the same length, but then the Young's modulus is 2 times E, but the cross-sectional area is A over 2. Okay, so immediately see that the extension for Q is going to be the same as the extension for P. Okay, so the correct option is C. Okay, I hope this makes sense. Now let's move on to question number 9. The acceleration time graph for the motion of an object is shown. Which of the following could be the displacement time graph for the motion of the object? Okay, so let me use a clean page to explain this. So the area under the curve gives delta V, okay, because acceleration times time is equal to a velocity. Okay, so the velocity time graph is going to look like this. So the velocity time graph would look like this. You have some accelerated motion with constant acceleration, okay, and then the acceleration drops to 0. I mean, this is what's implied from this graph that the acceleration drops to 0, right? Therefore, with 0 acceleration, the object is going to continue with the same velocity, okay? So this will be the velocity time graph. And from this, we can construct a displacement time graph, okay? So the displacement time graph will begin with a parabola, right? Because we have acceleration, okay? And acceleration is given by 1/2 at squared, okay? So we're gonna have accelerated motion. So options C and D are promising, but then when the acceleration drops to 0, okay, the velocity is constant. Therefore, we will observe something like this, okay? Because I remember that the gradient of the displacement time graph, the gradient, is equal to the velocity. And in this case, we have a constant velocity if it's a straight line. So C is not the correct answer, actually. So D is the correct answer, okay? Again, this is another difficult problem, guys, okay? So I don't know why they made section A for this paper so hard, but yeah, I thought it was hard. Okay, I hope this makes sense. If it doesn't, ask me and I will provide further explanations if needed. Right, okay, question 10. Two objects R and S are falling vertically and accelerating due to gravity. Air resistance is negligible. R has mass m and S has mass 2m. Initially, each object has momentum p. After time t, object R has momentum 2p. Which of the following gives the momentum of object S after time t? Okay, we can work with object R, okay? So it says that initially it has momentum p, okay? So p is simply mass times some velocity v, okay? And after some time t, it has momentum 2p, which means that the mass is not going to change. So so the velocity pretty much doubles, right? So we can write that this is equal to v prime. So 2p is m times v prime. So v prime, the new velocity, is going to be 2p over m, which is simply 2v pretty much, okay? So after time t, r has momentum 2p and 2v is the velocity, okay? So its velocity changed by v in falling through the gravitational field, okay? Now for object S that we are interested in, so S also has momentum p, but its mass is 2m. So 2m times its velocity gives p. So its velocity is going to be half the velocity of r, pretty much. I hope this makes sense, right? So because they have the same momentum. So the momentum is m times v as well for S. But you have to remember that, actually, no, I'm not going to write this. So in order for object S to has momentum 2p, so 2p, to has momentum p, excuse me, since the mass is 2m, its velocity is necessarily v over 2, okay? After time t, S will also change its velocity by v, because both fall in the gravitational field. And remember, when something falls in the gravitational field, its final velocity does not depend on its mass. So if they start with the same momentum and they spend the same time t in the gravitational field, they will both increase their velocity by v, okay? So the final velocity for S is going to be v plus v over 2, which was the initial velocity, which is 3v over 2. So p for object S is going to be 2m times 3v over 2. So it's going to be 3p pretty much. Okay, so the answer is actually B. I hope this makes sense. If it doesn't, another thing that can help is you can use v squared is equal to u squared plus 2gs, and then no, it's not gonna help. So no. I don't want to confuse you. I want to keep it simple like this. So I hope this makes sense. If it doesn't, ask me in the questions, but in the comments. But again, the way to see how this works is to realize that because initially they have the same momentum, right? Then the heavier object needs to have half the velocity so that the momentum are the same. And since the velocity of r increases by v, okay, after time t, object S will also have the same change in velocity. Therefore, the final velocity for object S is going to be 3v over 2. And because the mass is 2m, the final momentum is going to be 3p. I hope this helps. If you can think of a better or faster explanation, let me know in the comments. But again, this section A was really hard, I think. One of the hardest I've seen. So, section A is done. We are ready to move on to section B. Okay, question 11. A lorry has a mass of 4,500 kilograms. The forward force on the lorry is 6,700 newtons. The total resistive force on the lorry is 900 newtons. Calculate the acceleration of the lorry. Okay, and these are words 2 marks, so it should be an easy problem. So let's see. So let's assume that the lorry is a square, a box of some sort. And assume this is the ground. So we are told that this thing experiences a forward force F equal to 6,700 newtons, a resistive force that is going to be backwards, let's call it R, with a value of 900 newtons. And we need to find the acceleration. So it accelerates in this direction. So the direction to the right is the positive, okay? So we have that F minus R is going to be equal to the mass of the lorry. By the way, in America, I never heard of the term lorry. They always call them trucks. So it's an English thing, I guess. So M times A. So A is F minus R over M. So this is equal to 6,700 minus 900 over the mass, which is 4,500 kilograms. And this is 1.28 meters per second squared, which you can approximate to 1.3 meters per second squared. Okay, not a very high acceleration. So let's move on to question number 12. A sailing boat is moving through water. The force of the wind on the boat is 350 newtons towards the north. The force of the water on the boat is 410 newtons at an angle of 120 from north as shown. Determine the magnitude and direction of the resultant force on the boat using a scaled vector diagram. Okay, so I will need to bring up the ruler. Okay, I'm not really fond of these types of exercises, to be honest. Okay, so okay, it's 350 newtons. We will say that this distance here, okay, we will call that, can I write there? No. Can I write here? Okay, so that's 50 newtons. Oops. Again, so that distance is 50 newtons. Okay, so for 350, we will need, no, that's too much. No, let's make this 50 newtons. Okay, I don't want to run out of page. Okay, so, all right, so 50, 100, 150, 200, 250, 300. So that's 350. All right. Now the other force is 120 degrees this way. Can I turn this ruler? Yes, okay. Okay, we need 120, right? Is this measuring though? Okay, let me see. Let me think. So that's 90. No, actually, we have to turn it this way, maybe. No, this is strange, guys. Okay, 180 means, let me think. So, oops. Okay, maybe this is okay. 120, is that it? Does it look right? It doesn't look right to me for some reason, but okay, so no, I have to parallel transport this. This is hard, guys. This is really hard to do on an iPad, but I'm doing my best here. Okay, so let's assume that's 120 degrees. Is it? No, it doesn't look right to me. It doesn't look parallel to that. So 120. So where does this start measuring from? Okay, set angle. So let me think. Let's do 150. Yes, okay. So now this is parallel, and the reason is because okay, you will have to believe me that that's 120, guys. Yeah, it's parallel. So we need, so oops, not that, this. So we need, that's 50, 100, 150, 200, 250, 300, 350, 400. So 410 is roughly that vector. Okay. Okay. And now what we have to do, that we drew it. Okay, I'm gonna remove this ruler for a while. Okay. So I use the parallelogram rule. So you have to draw a parallel line and another parallel line like that. And this is what you're looking for. Okay. All right. And now we will have to bring back the ruler and measure the size of this vector. I'm pretty sure this is the most terrible explanation I had in this channel so far. But okay, let's measure it. So, okay, so it looks like it's 50. Okay, so 50, come on, it's not writing. Why? Okay, I can't write for some reason. So it seems like the length of this is what? So that's 50, 100, 150, 200, 250, 300, 350, 380, something like that. Okay, so 380 newtons. And okay, if you bring the ruler there, it says 0. Okay, so if we turn it this way, it says 20, but it's not really 20. What they really mean, it's actually 22. So it's actually 90 minus 22. Okay, so this angle is going to be, what is it, 90 minus 22? 68 degrees. Okay, I didn't enjoy this problem at all, guys. I did my best to explain it, but I guess it's easier to do on a piece of paper instead of an iPad. Okay, so I did my best. So yeah, okay, let's move on. I don't want to discuss about this problem anymore. Okay, let's move on. Okay, question 13. A student used two different methods to investigate the acceleration of a freely falling object. In the first method, the student dropped a ball from rest at a known height. He used a stopwatch to measure the time taken for the ball to reach the ground. He repeated this several times. He then calculated the mean acceleration of the ball. Explain why there was a large uncertainty in the calculated value of acceleration. So let's start by writing that starting and stopping, okay, the stopwatch by hand, involves human reaction time. Involves human reaction time. Okay. This introduces a large random error into the measurements. Those errors carry into the calculated acceleration. Okay, this is the explanation. So let's move on to part B. In the second method, the student positioned light gates near the top and bottom of a transparent vertical tube. He dropped a metal cylinder into the tube as shown. Okay, we see the metal cylinder, so it's gonna move this way down, okay? The time taken for the metal cylinder to pass through each light gate was recorded by a data logger. The student measured the distance between the light gates. Give one other measurement needed to determine the acceleration of the metal cylinder. So the student measured the distance between the light gates, so this distance, okay, which is the height, I guess. So the only other measurement that you need is the length of the metal cylinder, so you can calculate its velocity when it passes through the gates. So you need this, let's call it S, okay? So you need the length or height, the length S of the cylinder, of the cylinder, which you need, let's use a clean page, which you need to determine VI and VF, the initial and final velocity, or you can call them U and V if you want. Okay. Now, part 2. The speed of the metal cylinder through the first light gate was 1.39 meters per second. Through the second light gate was 2.96 meters per second. The distance between the light gates was 355 millimeters. Calculate the acceleration of the metal cylinder. So we're going to use suvat equations since we are dealing with constant acceleration, which is g, right? So v squared is going to be u squared plus 2as, okay? And we are interested in a, which is of course g. So a is v squared minus u squared over 2s. So 2.96 squared minus 1.39 squared over 2 times 355 times 10 to the negative 3, I'm sorry, because this is in millimeters. So minus 3, and this yields 9.62 meters per second squared. So kind of close to 9.81, which is G. All right, so let's move on to question 14. Two rocks in outer space are moving at different speeds along the same path. State the principle of conservation of momentum. So in a closed system, the total momentum is conserved, okay, provided no external forces act on it. Okay. All right, so part B. Rock A has a mass of 43 kilograms and a velocity of 7.8 meters per second. Rock B has a mass of 56 kilograms and moves in the same direction as rock A. The kinetic energy of rock B is 4.1 times 10 to the third joules. Rock B collides with rock A. After the collision, rock B continues to move in the same direction with a momentum of 530 kilograms times meters per second. Calculate the new velocity of rock A. Okay, let's write down, actually let's use a clean page. So we have the mass of rock A is 43 kilograms. The velocity UA of rock A is 7.8 meters per second. And therefore, we can use these two to find the initial momentum of rock A as 335.4 kilograms times meters times seconds to the minus 1. Now for B, we have that the mass of B is 56 kilograms. We are not given the velocity, but we are given the kinetic energy of B, which is 4.1 times 10 to the third joules. Okay, so we can find the velocity. 1/2 m times ub squared is equal to the kinetic energy of B. Therefore, ub is going to be the square root of 2 times the kinetic energy of B over the mass of B. So this is going to be equal to the square root of 2 times 4.1 times 10 to the third over 56 kilograms. Excuse me. So 12.1 meters per second is the speed of B. And we can actually calculate, let's box this because we will need it. We can now calculate the momentum of B before the collision as 677.6 kilograms times meters times seconds to the minus 1. Now the situation is the following. Let's use another clean page. So you have B moving faster than A in the same direction. So both move in the same direction. This guy moves with 12.1 meters per second, and this guy moves with 7.8 meters per second. So this is before the collision. And then after the collision, they will keep moving in the same direction pretty much. Okay, so B will move in the same direction as A. And we are actually given the momentum of B after the collision. And this is equal to, where is it? 530. Oops, I don't know why I did that. So PB prime is 530 kilograms meters per second. Okay, so we have all the momenta. We calculated all the momenta, and we are looking to find the velocity of A after the collision. So the momentum before the collision, PA plus PB, is equal to the momentum after the collision, PA prime plus PB prime. Okay, excuse me. So PA prime is equal to MA times VA, right? And it's simply equal to PA plus PB minus PB prime. So VA is simply PA plus PB minus PB prime over MA. For those of you who are watching my videos, you know that I always like to reach a final expression using algebra and then plug in numbers. So now is the time to plug in the numbers. We calculated everything earlier. So 335.4 plus 677.6 minus 530 over 43, and this yields 11.23 meters per second, which is the final velocity of rock A. And we see that its velocity actually increases, okay? Which makes sense because it collided with something that moved faster. In space, by the way, so no gravity. All right. This kind of questions are in vogue with space because I think Artemis 2 is going on, and all these developments with space exploration are kind of rekindled after the 60s. It's been so long. I mean, the space race was in the 60s between the Soviet Union and America at the time, the only two players. Now you have everybody. So you have America, of course, again. Now you have China, Japan, Europe. Who else? India. Who else is involved in this? Russia, of course. If I'm forgetting anyone, let me know. But yeah, this is what comes to mind just off the top of my head. All right, let's move on to question number 15. The game starts in 2 hours, so I have to speed up. Okay, question 15. A student investigated a spring. The student measured the unstretched length of the spring. The student suspended different objects from the spring as shown. She measures the new length of the spring each time. So we have the spring, ball, and 200 grams mass. Question A, the unstretched length of the spring was 0.25 meters. When the ball was suspended from the spring, the length of the spring was 0.295 meters. When the 200 grams mass was suspended from the spring, the length of the spring was 0.375 meters. Calculate the weight of the ball. So, okay, let me think about this. So the length, is 0.25 meters. L prime, the length of the spring, is 0.295 meters when we hang the ball, which means that delta x for this case is 0.045 meters. Let's call it prime, delta x prime. And then L double prime is 0.375 meters when we hang the 200 grams of mass. So delta x double prime is 0.125 meters. Okay, so when we hang the mass of 200 grams, which is 0.2 kilograms, so 0.2 kilograms times g is k times delta x double prime. Okay, so k, we need to find k first of all. Okay, so k is 0.2 times 9.81 over 0.125, so 15.7 newtons per meter. And now the weight of the ball is going to be equal to k times delta x prime. So we have 15.7 times 0.045. This yields 0.71 newtons for the weight of the ball. Okay, that's that. Let's move on to the other part of the question. The sketch graph shows how the extension delta x of the spring varies with the total force F on the spring. Explain why the elastic strain energy stored by the spring is proportional to F squared. So the area under this curve, so this area pretty much. So the elastic elastic strain energy stored is equal to the area under the F versus delta X curve. Okay, so the elastic energy is simply 1/2 F, F times delta X, which is this area that I drew with a red color, right? It's the area of a triangle, so 1/2 F times delta X. But F is K times delta X, right? So we can plug in and find that the elastic energy can also be written as 1/2 times F over K. And this is delta X pretty much, right? So this is equal to 1/2 F squared over K. Therefore, the elastic energy is proportional to F squared, which is what they ask us to prove, and we proved it. Okay, it's very rarely used. I don't know why they asked this question here, but yeah, okay, that's that. Let's move on to the next question. Okay, question 16. The photograph shows an athlete using a running blade. Okay. The value of the Young modulus for the material used to make the running blade is 19 gigapascals. I state which property of the material relates to the Young modulus. It gives us the stiffness of a material. Okay, so stiffness of the material is the answer. All right. 2. A sample of the material has a length of 0.45 meters. In a laboratory test, a compressive stress of 150 megapascals is applied to the sample. The sample deforms elastically. Determine the new length of the sample. So stress is equal to strain times the Young modulus, and strain is delta x over L times the Young modulus. So delta x is stress times length over the Young modulus. So if we plug in numbers, we have 150 times 10 to the 6, and this is pascals, times the length, which is 0.45 meters, over the Young's modulus, which is 19 times 10 to the 9, and this is pascals. So pascals cancel. Again, whenever I plug in actual physical units, I put all the units to the right and all the numbers to the left, so you can work easier with these kind of things. So this calculation gives 3.55 times 10 to the negative 3 meters. So the new length, let's call it L prime, is going to be L minus delta x. Why minus? Think about it and let me know in the comments. Pause the video, whatever. Okay, the reason is that we are compressing it. Okay, compressive stress. Okay, so therefore the length will reduce. Okay, so 0.45 minus 3.55 times 10 to the third yields 446 meters. Okay, so which is our answer. Part B. The running blade is made from a single material. The table shows the compressive breaking stress of 3 materials used to make different running blades, and they give us the breaking stress for glass fiber, carbon fiber, and hybrid fiber. The cross-sectional area of the running blade is 8.5 square centimeters. The maximum compressive force that can be applied to the running blade before it breaks is 330,000 newtons. Deduce which material the running blade is made from. So stress is force per cross-sectional area. So the maximum compressive force is 330,000 newtons. The cross-sectional area is 8.5 square centimeters, so 8.5 times 10 to the negative 4 square meters. Okay, and this is because 1 cm is 1 times 10 to the negative 2 meters. So 1 cm squared is that thing squared, so 1 times 10 to the negative 4 squared meters. Okay, so this calculation yields 388.2 megapascals. Okay, so the only material that can work from the ones that are given to us is carbon fiber. Okay, so carbon fiber, because sigma breaking is 400 megapascals, which is larger. Oops, I created this mess again, I'm sorry. So because sigma break is 400 megapascals, which is larger than the largest applied force, stress of 388.2 megapascals. All right, so this was question 16. Let's move on to question 17, I believe, right? Yes. So again, I didn't expect, and I sound arrogant now, but I didn't expect to learn new things while solving these past papers from Edexcel, but I do learn new things all the time. So one of them is the lifting bug. I never heard of this thing before, and I live in an island. I'm surrounded by sea. So most people call it paradise. I call it a prison, okay? Because if you read history, if you're into history, you will realize that the strictest, the most brutal prisons were always on islands. So Alcatraz is an island outside San Francisco, which was a notorious prison. Then what else was a prison? Chateau d'If, it's in Marseille. That was the prison where they jailed Count Monte Cristo, okay, from the novel. Australia is an island and was a prison, kind of. Forgive me if you're watching from Australia. So you get the idea. So I think Cyprus to be a prison, okay? So anyway, a lifting bag is a bag that can be filled with air and used to lift heavy objects from the bottom of the sea. It's brilliant, I have to say. It's brilliant, but I never heard of it before. So lifting bags are attached to an object and then filled with air. A person attaches two spherical lifting bags to a box at the bottom of the sea as shown. Okay, not to scale. We see the lifting bags. So they look like humans, so we can make them smiley faces. So a boy and maybe a girl. Okay. Oops. Yeah. Okay. So something like this. All right. The total weight of the box and two lifting bags filled with air is 2,500 newtons. The diameter of each spherical lifting bag is 50 centimeters. Deduce whether the box will lift from the bottom of the sea, and they give us the density of seawater. So this is a strange kind of problem, but okay, we pretty much have to compare the total upthrust against this weight, okay? Because that's the total weight of the box and the two lifting bags. So the total upthrust, this is going to be equal to the upthrust for the box. So the upthrust is going to be the density of the water, because the displaced volume is in this case the displaced water, right? So the density of water times G times the volume of the box. So that's the upthrust of the box, plus 2 times the density of water times G times the volume of the bags. Okay? If this doesn't make sense, ask me in the comment section and I will reply. So the density of seawater is 1020, G is 9.81, volume of a box is 0.25 times 0.5, times 1.1 plus 2 times, again, same density, same G, we are on the same planet still, okay, times the volume of these bags, so 4/3 pi times the radius, which is the diameter is 50 centimeters, so 25 centimeters, so 0.25 meters cubed, okay, and this yields 2,685.7 newtons, which is larger than 2,500 newtons. So it will work. So the smiley faces were the proper faces to draw, because if it wasn't enough, if the upthrust wasn't enough, I would have to maybe make them sad faces. So let's move on. Part B. As the person filled the lifting bags, a small bubble of air escaped and moved upwards through the seawater. Calculate the terminal velocity of the bubble of air predicted by Stokes' law. Okay, so this is a little bit tricky in that you have, okay, let's make it smaller. Okay, so this is the bubble, I guess, and it moves up. Okay, so the upthrust is obviously up, but the drag force is in the opposite direction. Okay, don't forget that. Okay, so the object is moving up, so the velocity is up, so the drag is in the opposite. The drag is always in the opposite direction of the velocity. Okay, and of course you have the weight of the bubble. Okay, so for terminal velocity, so for V terminal, we need, let me draw an arrow. Okay, we need the upthrust to be equal to the weight plus the drag force. So the drag force is going to be equal to the upthrust minus the weight. Now the drag force is 6 pi times the viscosity times the radius times the velocity, and this is equal to the upthrust minus weight. So the velocity is going to be upthrust minus weight over 6 pi times the viscosity times the radius. Okay, and I'm gonna move back to a clean page. I'm over here. Okay, so we are given various things which we will take advantage of. So 4.77 times 10 to the negative 4 is the upthrust. The weight is 1.82 times 10 to the negative 6. Okay, and then we have 6 pi times 8.6 times 10 to the negative 4 times 2.25 times 10 to the negative 3. So this yields 13.03 meters per second, which is approximately just 13 meters per second, which is kind of fast. I have to say, I was impressed. Okay, 13 meters per second, just to give you perspective, is faster than Usain Bolt. Okay, because in 10 seconds, this bubble is going to cover 130 meters. Okay, think about that. So, part 2. Give 2 reasons why the terminal velocity of the bubble may be different from the value predicted by Stokes' law. So it might not be, maybe it's not a perfect sphere. Okay, that could be one reason. Another reason is that the flow around the bubble, excuse me, around the bubble might be turbulent. Okay, and other reasons could be that the volume of the bubble might change due to pressure, right? And recall that, okay, since I come from the sea, we mentioned that, as bubbles rise, do they get smaller or bigger? Let me know in the comments. And I'm actually not gonna say it. I'm not gonna say the answer. I'm gonna reply to the first comment or any comments commenting on whether, okay, let's say I am diving into water and I'm 20 meters down, something like that, I don't know, and I let the bubble of air out. Is it gonna get larger as it rises or smaller, and why? Okay, let me know in the comments. So, and the viscosity might change. So viscosity might not be constant. Okay, constant due to temperature differences. Okay, so these are some reasons that you can write. Okay, so 18, in the sport of bicycle motocross, BMX, a person rides a bicycle over small hills and ramps. A person rides a bicycle to the top of a hill with enough speed for the bicycle to leave the ground. The diagram shows 3 stages A, B, and C of the motion of the bicycle. So you have constant acceleration, constant velocity, and then the bicycle leaves the ground. In stage A, the bicycle moves with constant acceleration on a horizontal surface until time TA. In stage B, the bicycle moves with constant velocity up a curved ramp until time TB. In stage C, the bicycle leaves the ground. Complete the sketch graph for stages A and B, and this is a distance versus time graph. Okay, so up to time ta, it accelerates, so it's going to be a parabola, right? And then from time a to time b, the distance, it moves with constant velocity, right? So I'm trying to, okay, let me raise this and try to make a better graph. So we have a parabola up to ta, okay? And then whatever the gradient of that parabola was is going to continue until tb, okay? So something like that. So what I'm trying to say is that the gradient gives the velocity, right? So the velocity is 0 in the beginning, then it increases, and then whatever the velocity was at ta, it's going to be the same at tb. So we continue with that gradient, okay? So this is what I'm trying to sketch there. All right, let's move on to part b. This is a long writing problem now. Explain how the useful power output of the person varies through stages A, B, and C. You should consider energy changes during each stage. Assume that air resistance is negligible. Okay, so let's start with stage A. Okay, so stage A, bike accelerates, right? So speed increases, right? So kinetic energy is proportional to v squared. So kinetic energy increases. So useful power output increases. Okay, this is stage A. Stage B. Okay. So V is constant. So Ki, the kinetic energy, is constant, right? Bike gains potential energy, so gains height. So GPE increases, okay? So person does work against gravity, okay? So the rate of energy, let me think. So the rate of, let me think, the rate of energy transfer, okay, it's the best way to put it, transfer to GPE increases, okay? So useful power output increases. Okay, so this was stage B. Now stage C, okay, the bike leaves the ground. Bike leaves the ground, okay. So the person is not doing work, okay. So the kinetic energy decreases because eventually it stops, right? So kinetic energy decreases, so GPE increases, okay. But useful power output is 0. And this is because the person is not doing anything. He's just on the air, right? So, yeah, I think we covered it all. It was a little bit tricky. I mean, I think this was a difficult problem, okay? So let's keep on moving. Question 19. Sport of shot put, a person launches a heavy ball called a shot into the air. The photograph shows a person about to launch a shot. The shot is very dense and has a large mass. Explain why the equations of motion can be used to give an accurate prediction for the path of the shot. So shot is dense and has large mass. Okay. So the air resistance is negligible compared to the weight. Okay. So only force acting is gravity. Okay. So the acceleration is equal to g and is constant. Okay. So suvat equations assume the acceleration is constant. Okay. So we can use them. And for those of you who are gonna go on to study physics or engineering at the university level, you will see that the suvat equations are special equations only applicable to situations when the acceleration is constant. So, or zero. I mean, zero is also a constant, right? So, but in real life, we have situations in which the acceleration changes with respect to time. And that's actually called a jerk, okay? So it's kind of funny, but that's the name. So when the acceleration changes with respect to time, it's called a jerk. So let's move on to the next question. B. The shot was released from a height of 1.85 meters above the ground. The shot traveled a horizontal distance of 14.2 meters before landing on the ground as shown. The shot moved through the air for a time of 1.61 seconds. Show that the horizontal speed of the shot was about 8.8 meters per second. So in the horizontal direction, remember we can break the motion into two independent motions in the horizontal and vertical directions. I mentioned this in my videos related to suvat and other past paper solutions. So the horizontal distance is equal to the horizontal speed times time plus 1/2 times the horizontal acceleration times t squared, but horizontally we have no acceleration, so we can delete that term. So v horizontal is equal to the s horizontal over time. So that's 14.2 times 1.61. So that's 8.82 meters per second. Okay, question 2. Determine the velocity of the shot at the point it was released. So they mean the magnitude here. Okay, it's kind of tricky and not clear the way it's asked, but okay, let's find the vertical velocity. So in the vertical direction, we have that s vertical is equal to v vertical times time plus 1/2 the acceleration in the vertical direction times t squared. Okay, now what's the distance in the vertical direction? The man is 185 meters tall, but and the shot put ends to the ground. So the horizontal, sorry, I keep saying horizontal, I mean vertical. The vertical distance covered is minus 1.85, and this is equal to the vertical velocity times 1.61, right? Plus 1/2 times the vertical acceleration, so minus 9.81, right? Times 1.61 squared, okay? And if we solve this equation, we will find the vertical velocity to be 6.75 meters per second. I will need a clean page. Therefore, the velocity is equal to the vertical velocity squared plus the horizontal velocity squared, which is 11.11 meters per second. And if we do this triangle, this is v vertical, this is v horizontal, this is the v we found, the magnitude. And we can also find this theta, this angle. They don't ask for it, but I think it's implied. So the tangent of theta is equal to the magnitude of the vertical velocity over the horizontal velocity. So 6.75 over 8.82, which is equal to, which gives an angle of 37.43 degrees, which is the answer. Okay, this was problem 19, and we are ready to move on to the next one, which is the last one, I think. So, okay, question 20. The photograph shows Tower Bridge, a bridge in London. The middle part of the bridge can be raised in two sections to allow boats to travel along the river. Each section can rotate about a pivot. So you have the section of the bridge, the pivot. State what is meant by the principle of moments. So for an object in equilibrium, the total clockwise moments about any point, about any point, and I'm gonna need a clean page, about any point is equal to the total anti-clockwise moment about that point. Okay. B. To raise a section of the bridge, a motor applies a moment about the pivot. The diagram shows a section of the bridge being raised. So you have the pivot, the center of gravity, okay? Explain the direction of the moment about the pivot caused by the motor as the section is raised. So we will have the weight, right, that causes a clockwise moment, right? So the motor has to provide an anti-clockwise moment. So something like that, okay? Or if you're in this direction, something like that. So let's write the answer. So weight creates a clockwise moment. Moment. So the motor needs to provide an anti-clockwise moment. Okay. Part 2. It's each section of the bridge has a heavy counterweight fixed to one end as shown. So, okay. Explain how adding the counterweight affects the work done by the motor to raise the section of the bridge. So, the counterweight is to the left of the pivot. Okay, so it creates an anti-clockwise moment. Okay, because it pulls, let me think. So the weight creates a clockwise moment and the counterweight is here. So it tends, wait, let me think. So this pulls down. Wait, I'm confused now. So yeah, the counterweight wants to flip the pivot in the opposite direction than gravity, so anti-clockwise. Yes, okay. So anti-clock moment opposes the clockwise moment by the weight, the clockwise clockwise moment by the weight. Okay, motor needs to provide a smaller moment for equilibrium. Okay, smaller moment means smaller force, so less work. Okay, so this was part 2. And the final part, the section of the bridge is uniform. The pivot is 12 meters from one end of the section of the bridge and 33 meters from the other end. The perpendicular distance from the center of gravity of the counterweight to the pivot is 11 meters as shown. A bus was moving across Tower Bridge when the motor began to raise the section of the bridge. When the center of gravity of the bus was 28 meters from the pivot, the section of the bridge was in equilibrium. Determine the magnitude of the moment produced by the motor on this section of the bridge. Okay, and they give us the weight of the bus, the weight of the section of the bridge, and the weight of the counterweight. So, okay, so the weight of the counterweight, so we control the forces, so the counterweight is gonna create an anti-clockwise moment. Then the bus is going to be 28 meters, so maybe there. So it's going to provide a clockwise moment. Okay, so that's 28 meters. And then what other forces do we have? Okay, the motor, we're going to account for it later. And we also have the weight of the bridge, which is going to be the center of mass of the bridge is at 33 plus 12, 45 over 2, 22.5 meters. So maybe there. So this is 22.5 meters. And that's the weight of the bridge. So weight of the bridge. Okay, so pretty much the weight of the bridge is going to be applying 10.5 meters away from the pivot. Okay, so we take moments about the pivot, this point over there. So we have 4.6 times 10 to the 11, which is this force from the counterweight, times the distance, which is 11 meters, right? Plus the moment of the motor that we want to find, right? Is going to be equal to 71,000, this guy. So 71,000 newtons times 28 meters, plus this guy, which is the weight of the bridge, 1.2 times 10 to the 7 newtons times 10.5 meters, we said it earlier, right? Okay, so if we solve for M motor, we will find 83.99 times 10 to the 6 newtons times meters, which is approximately 84 times 10 to the 6 newtons times meters, which is the answer. All right, this was a long Unit 1 paper. I think it was hard, but I have an hour and 30 minutes to edit it, eat, have a shower, and watch the game. So I hope this video is useful, and I hope it comes out at the right timing. Let me know what you think in the comments, and please subscribe. Most of you watch the videos without subscribing. Subscribing is free. I'm not asking for anything. So yeah, that was the video. See you in the next one. Bye.